Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to talk about generalization. We'll talk about what generalization is, we'll talk about why we have to generalize, and then in the next sort of video or video series, we'll talk about specifically how we generalize. So with generalization, just like when you generalize in other facets of your life, what we're doing is we're taking something and we're reducing the complexity, or we're reducing the level of detail so that it's more broad, right? But in specific with cartographic generalization, what we typically refer to is this idea of a process, right? So it's the process or processes, because we'll talk about multiple different ways that we can generalize, right? But it's the process by which we reduce the level of detail right, the level of detail in a spatial data set right, due to needs such as, right, a change in scale, so you can imagine maybe you go from a large scale map to a small scale map, right? Maybe it's the map purpose, right? You would need much more detail if you're producing something for, say, a city planner or an architect than you would if you're making a map for like a child to use at a zoo, right? Or, right, other limitations. This other limitations, a big one might be right, hardware. So right, if you have a very large data set, because at the end of the day, spatial data, right, one of the things that drives the data size is the number of points, right? So if it's points, it's just points. If it's lines or polygons, it's the number of nodes, right? The more nodes or points you have, the larger the data set is. And if you have a data set with a lot of complicated features, it's going to be a large data set. And maybe you have a computer that you're trying to process data on that simply can't handle that large of a data set. And so you have to simplify it to reduce the data volume. So that's an example of like an other limitation, right? So I'm just going to make a note here of like, say, maybe data volume. Maybe your data set is just too large, right? So that's what generalization is, right? It's the process by which we reduce the level of detail in a spatial data set due to needs such as a change in scale, map purpose, or other limitations such as hardware. Now, in the intro, right, we talked about sort of 4 key ways or things that these changes cause that force us to make decisions about generalization. And it was the 4 C's, right? We have congestion, right? We have coalescence, we have conflict, and we have complication. So let's go ahead and talk about each one of these in order, kind of describe them, and look at an example of what that might look like on a sort of a fake map. So let's talk about congestion first. Right, what is congestion? Congestion occurs when you have a change in scale that puts too many map elements, or not map elements, too many features into too small of an area. So this is typically when a change in scale, right? And again, so this would be large scale to small scale. When a change in scale results in too many features right, in too small of an area. So let's say we have a large scale map, maybe say 1 to 1,000. And I'm going to do this in blue just so that we're clear that this isn't writing. Right. And so we have our, right, maybe these are rivers. Right. And so you can see in the 1 to 1,000 scale map, right, we have a lot of space between the lines, right? But if we transition towards if we transition from a large scale map, right, to a small scale map, maybe say 1 to 1,000,000, right? And if we think back to scale, this is effectively, right, zooming out. Right, maybe in that new result, right, our rivers that were originally, right, pretty far apart are now, right, super close together. Even though technically, right, this distance between them hasn't changed, because we've zoomed out, right, the amount of space that distance takes up on the map, right, is now much, much, much closer together. And something that we didn't really talk about when we talked about visual variables, but it's important nonetheless, right, is that when we're representing spatial data on a screen, lines, points, and polygons, right, the outlines of them, the size of the actual symbols, take up space on the screen. So even though we're trying to represent this real world distance, right, as the same, if the lines are the same thickness due to the cartographic decision that we've made, this looks very, very congested, right? Right, this looks congested. So if we're trying to do something like maybe place labels or something, we're going to have a much harder time with it in this case than in this case. And so we would have to make a decision of, okay, what do we do to make less congestion here? So that's what congestion is, right? It's when we have the real world distances between things stay the same, but because we zoom out, it starts to clump things together and it looks congested. Taken to the extreme, right, congestion, we end up with something called coalescence. Right, we end up with something called coalescence. And coalescence is, right, when a change in scale right suddenly results in features right to overlap. So rather than just looking congested, with coalescence, they actually start to be on top of each other, right? Overlap is another word of saying be on top of, right? And so let's go ahead and do this, right? So let's say in this example, right, we have, right, two roads. Maybe this is like a freeway and a service drive, right? And in the large scale map, because again, right, we start off in the large scale, right? You can still kind of see that they're two separate lines. But when we transition to small scale, suddenly, right, because they were so close to begin with, well, now, right, it's impossible to tell them apart, right? There's two separate lines here, but you can't tell that. That's what coalescence is, right? This is still two lines, but they are on top of each other. Right. And again, you can think of coalescence as sort of an extreme version of congestion, where that change in scale is so abrupt or so extreme that you end up putting features visually on top of each other due to the fact that we still have visual variables representing these things. So we would have to figure out kind of how do we solve this, right? How do we make it so that these two lines are visible, or do we get rid of a line, right? What sort of generalization steps do we take? So similar to coalescence, we have this idea of conflict, right? This idea of conflict. So conflict is usually when you actually have two data sets kind of working together, and you run into an issue where the generalization of one data set causes something to be wrong or be in conflict with reality in another. When changes in scale cause a cause a feature in a map to conflict with reality. Right. And so the best example I could give, right, would be, I'm going to do my best to sort of draw here. Right. So let's say at the large scale, right, we have this peninsula. Right, so this is a peninsula. Right, and then out here we have ocean, and here we have land, right? And then we have a point right here, right? That, right, maybe is a city, right? So it's a city on a peninsula. And this is, again, large scale. Right? When we convert that to small scale, so we zoom out, right? And we generalize the shoreline, which we'll talk about kind of how to do that, right? So we've generalized the shoreline. So this is now a generalized shoreline. Right, you'll see that we've gotten rid of most of this peninsula because we generalized out a lot of the points, and we'll talk about how we do this later, right? But we generalized out a lot of these points. So now, right, our city, our point that represents our city, is now kind of out in the middle of the ocean. Right? And this would be, right, a bad thing. We don't want this. So we now have to figure out, okay, what do we do with our city? What kind of generalization technique do we do with our city to address the fact that our shoreline has been generalized and it's now created a break with reality where visually now our city is in the ocean. which logically doesn't make sense, right? We don't typically have cities in the ocean. So that's what conflict is, right? It's when we change the map scale or we change something, right? We generalize a data set and it causes features in another data set to break reality in the map, right? Because in the map, we're showing a city in the ocean. In reality, we know that it's not, but visually, this just doesn't make sense. That's what conflict means. So finally, we have what is probably in my opinion, kind of the hardest one to kind of wrap my head around. And that's this idea of complication. And complication really results when you have abrupt changes, and I'm going to use the term complexity in complication, right? When you have an abrupt change in complexity, right? And I guess to put a loose definition on what I mean when I say complexity here, I'm going to say the number of vertices. Right? Between parts, between different parts of a feature. Right? And so, for example, let's say that we have a road or a freeway, right? And the freeway kind of goes straight, and then all of a sudden it hits an area where there is a lot of terrain. And so the people building the road suddenly had to do kind of this to kind of make up for the fact that, hey, there's mountains and all kinds of stuff, right? This tonal shift, and I'm going to put a green line here to kind of show you what I'm talking about. Right? The shift in complexity, right? From this side to this side, right? That can be jarring on a map. And it may not necessarily be clear to the viewer as to why that is, right? And so we may feel an urge, right? May want to consider. That is a terrible bracket, but that's fine, right? Or you may want to consider generalizing, right? This side, right? We may want to consider removing complexity. We may want to consider removing complexity from this right-hand side here, because the level of complexity here is so much more than the level of complexity here, even though it's the same feature. So hopefully complication makes sense. It's a little bit different than the other ones because it's not necessarily caused by changing anything. It's just a comparison within a data set or within a feature where you have part of the feature or some of the features are relatively simple and other parts or other features are extremely complex, and it can be very jarring, and you may want to kind of address that issue so that you don't have this just sharp tonal shift from relatively straight and simple to all of the sudden, right, immense levels of variation and complexity. So again, just to review, generalization is this idea that we have to reduce the level of detail because we have some sort of change in scale or a different type of map, purpose, intention, or some other technical limitation. Typically, those changes lead to either congestion, coalescence, conflict, or complication that are the sort of technical drivers for why we would need to do some sort of generalization. So in the next videos, we'll talk about how we generalize, if that makes sense. So hopefully there aren't any questions, but if there are, as always, please reach out. Thank you.